Hello everybody. Today we're going to do the hypothesis test for the mean given we know the population standard deviation. And that's very important that we understand that we know the population standard deviation. Well, what I would do is every now and then pause the video, take a picture of my screen so you understand some of my details. For example, these are the steps I'm going to follow in my hypothesis test 1 through 9. Every now and then, a person can do 10, 11, and 12 if they'd like. But the core heart and soul of hypothesis testing is 1 through 9. All right, to do this correctly, hypothesis testing, we need a scenario. So let's look at hypothesis test mean 1. And let's look at this example. See, in 2004, a study on ginkgo and ginseng as herbs to stimulate learning and memory happened. In the study, 25 participants took the herbs for 90 days. After the study, the participants took a standardized memory test, which has a normal distribution for the scores and an average of 50 points and a standard deviation 12 points. The participants scored an average of 54 points. So is there evidence, ITE, is there evidence at a 5% LOS, level of significance, that the true average memory is different based on using the herbs? Very good question. So how do I know it's a hypothesis test? Well, it's a hypothesis test because we're tracking evidence. And so the question would be, how does one perform a hypothesis test? It comes down to there are many hypothesis tests out there. We are looking at a hypothesis test for mean. If you read, it says, right, for the average. Now, right there, that tells me it's a hypothesis test for mean. On top of it, and in fact, I'll wait for step 2 to kind of go there. But first things first, I like to do my step 1. I like to label my null and my alternative. I like to start right there, the null and the alternative. So I go back to my question again. It says, is there evidence that the true average memory is different based on the herbs? So we have to know what the true average memory typically is, and that's 50 points if you read the paragraph again. And so what we know is we assume everybody has a memory of 50 points. And that's how you write that. We assume the mu, the population average, is 50 points. We want to show, utilizing the herbs, that it's not 50 points. That I don't know if it's higher or lower. It's just different. Using the herbs of ginseng, and I forgot the other one, ginkgo, the average would not be 50 points. Also in this step, I like to give my significance level. And if we look again, I believe the level of significance is 5%. And it is 5%. And by the way, just understand this is the probability of a type 1 error, in case you were wondering. As if you looked at one of my videos on the introduction to hypothesis testing, a person really typically wants to control the type 1 error. We'll talk more about that later. So to me, this is step 1, labeling out your null and alternative hypothesis, and also coming up with your alpha. From here, in order to do step 2, and that is choose the correct, and let's go to the steps here. Pick the correct formula, so that really should be step 2. What do I mean by pick the correct formula? Well, what I mean by picking the correct formula is I'm trying to understand, are we using a z-test or a t-test or something else? That's really what I mean by pick the correct formula. And so in some respects, I almost want to get rid of this statement. It's really understand the problem, right? Step 1 is understand the problem. And understand that it's a hypothesis test. So we just did step 1, we just did step 2. Now, we want to build critical regions. Well, to understand critical regions, we need to know what is our test all about. Well, what's very important here is the data. And in this data dump that I'm going to do quickly, I guess you can add that in, we know it's about average. So that means we probably have a sample average. And with the sample average, you probably have a count of how many people we studied. The key ingredient to this whole thing is, do you have sigma or do you have S? Because that really would determine if I'm going to utilize the Z or a T test. Let me read to pick off those variables again. So when I read this, we have a study of 25 participants. So that's our N. We studied the 25 participants. Got it. That's my N. And the participants scored 54 points on average. So that's my X bar. So I can see right away I have my N, one more time, 25 participants, and their average was 54 points. Got it. Now, do I have sigma, which is a population standard deviation, or do I have the sample standard deviation? Let's go back. Well, nothing in here mentions the standard deviation for the sample. This is really all I have on the sample. But I do have the test. The memory test is normal distributed and has an average and a standard deviation of 12 points. So this leads me to believe I have sigma. And so I have sigma is 12 points. With that known, I know right away, because I have my sigma, that means everything I do is going to be in terms of the z-test, the normal distribution test. So now I draw my rejection region. So what does my rejection region look like? Well, we know it's normal. It's normally distributed. It says the memory test is normally distributed, so we're good there. We don't need the central limit theorem. And if you notice, we don't have the central limit theorem because our N is under 30. But guess what? I don't care. It did say in the question, we're normally distributed. Please make sure you understand that. We have a normal distribution, not by the central limit theorem, because the darn thing said memory tests are normally distributed. All right, it said memory tests are normally distributed, which means I don't care the sample size you're using. Every sample size will be normally distributed, and that's awesome. Okay, I need to build my picture. So what's my picture going to look like? Well, there's some key ingredients here. There is my alpha and my not equal to. These are the two pieces that really help me build my critical region. See, what's going on is I have these two bars out here, and I'm trying to figure out the z values for which these bars live at. That's really what I'm trying to do. Is I got these two cutoffs. Why these two cutoffs? Because we're doing a two-tailed test. That's why. It says not equal to. And when you have a not equal to, you're doing a two-tailed test. The question is how far before we're allowed to reject? And that's where alpha comes in. Alpha is the area in total of the rejection region. Well, since alpha in this case is 5%, that means we have a whopping 2.5% for each side. The total area outside the rejection region should add up to alpha. And so that's how I draw my picture. So the question becomes, how does one find the z value, the critical value, as is called, the critical value for this picture? Really good question. The good news is, if you've come through my videos, you know exactly how to find this. This is nothing more. If you're trying to find a z value, is it norms s inverse or is it norms s dist? The answer is, hopefully, as you agree, it is norm.s.dist. Can we verify that? Sure. Let's go to Excel. If one goes norm.s.dist, look what comes up. It wants a z value. So actually, I stand corrected. We want, and if you're correcting me, that's awesome, we want norm s inverse. Because norm s inverse says, hey, you give me the probability below, and I'll find you the z value. This is why I always have a little cheat sheet next to me to understand what's going on. Actually, I don't use a cheat sheet anymore. I look at Excel. Excel for norm s dist said, give me the z value. I didn't have the z value. That's why I knew I was wrong. But if I use norm s inverse, it's asking for the probability. That I have. I know the probability below that z bar. Come on, guys. We played this game before. It is 99, right? If there's 2.5%, now think about this. For this z right here, there's 2.5% above it. If there's 2.5% above it, that means there's 975 below it, right? If you have 2.5% above this bar, then you have 97.5 below it. And that's the number you put in. You always put in the probability below the bar you want, and then norm S inverse will do the calculus needed to find your Z value. Awesome. So let's go to Excel. And the great thing is you can automate most of this in Excel as long as you understand some key components. First of all, it's a not equal to test. All right? It's a not equal to test. That's very important. That's kind of like my H1. My alternative is not equal to. So the next thing I realize is I'm going to need N. I'm going to need X bar. I'm going to need sigma. And if I have mu, it'd be nice to know that too. Well, we know mu. It said the typical average on a memory test is 50 points. The typical standard deviation is 12 points. The average of my sample was 54 points. And the number of people in my study is 25 points. So this is all the relevant information. And in fact, you can dump in alpha if you'd like to. Alpha, and I'd put it as a decimal. Alpha in this case is 0.05. 5% level of significance. With these ingredients, I'm able to, first of all, find what I call the critical values. So the critical values, or because it's a two-tailed test, I have to understand there's going to be two of them. And so with the critical value, what I would do, because it's not equal to, I would do norm.s.inverse. Notice it wants a probability. I now understand it's going to be alpha. It's going to be half of alpha added to the area in the middle, which would be 95, and so it's 97.5. Another way to look at this is I can find the lower critical region by using norm S inverse of 0.25. You could plug in 0.25, half of the alpha, because of the not equal to. That would be the lower end, which lets me know the upper end. So this would be the lower critical. The upper critical would just be the absolute value, ABS, of this number. Or another way to approach it is just like I said, norm.s.inverse of 0.975. And they should match, and they do. So I'm using a lot of symmetry and knowledge of our previous chapters, normal. If these are tough, go back to my videos on normal distributions to really understand how I understand the critical values. I got these two bars. How do I find them? Well, to find the bars, you use norm S inverse. That's very important. All right, I made a mistake before. These are the lower critical and the upper critical bars. And that will be the numbers I put in my picture. Honestly, a person should always draw a picture. Without pictures, without steps like this, you really don't have a really good discussion point. And so there is my critical value in critical region drawn. Let me make sure I'm going through our steps here. So we understand the problem. We stated this. We defined the critical regions, and that's what we just did. We defined the critical regions in this picture. So this was our next step. After loading in all the information, I'm able to define and build a critical region based on that information. 2 bars because it's a not equals to. The alpha is the area outside of both bars in this case. If there's 1 bar, all of alpha would go into the one extreme area of that 1 bar. We'll see that in a future example. There are 2-sided tests, there are 1-sided tests. Right now we're working on what is known as a 2-tail or 2-sided test. Now that I know the picture, I really recall my normal distribution. This is very important that we had a normal distribution because look what I used here for a code. I utilized the norm S inverse in Excel. Or you can use the normal table, your choice too. Look up 0.975 in the normal table and you will see 196 in there. It's one of those staples we memorize. 196. Awesome. Now, what we have here, the theory here is this is the region. In here, if when I collect my sample, it falls between these 2 points, then you don't have any evidence of rejection. It's when you get past these numbers that you reject H0. Going back to understanding what we're doing, well, we're setting down the ground rules to the game. If you end up in the red, you're going to reject H0. If you end up in the middle, you DNR. You do not reject H0. So if you're a test statistic, when you collect your sample and your data, and you fall in between the negative Z and Z in a two-tailed test, you're going to say, nope, I don't have any evidence that I'm different taking these herbs and having better memory. If you find out you're on one of the edges, then you do have evidence it's either improved or decreased, but you have evidence it's different. And that's what we're trying to do here, set up a picture so we can say, yeah, if my sample falls into here, then I don't have evidence I've improved, or I should not say improved, I have changed, because that's what I'm testing. I have any difference from the national average. Or if I do fall in the red region, I do have evidence that I have changed from the national average. Let's see what happens. So now we need a test statistic. Well, the test statistic, that's why you need to know which formula you're working with. You're working with the Z because you're dealing with sigma, right? We have sigma. This implies we use the Z statistic. And how do you find it? You look it up. The Z statistic is very well known. It's x bar minus mu divided by the quantity sigma over radical n. That's your Z value. That is our Z formula. Good news is you have x bar, mu, sigma, and n preloaded in Excel. So I'm just going to go to Excel and find my Z statistic. So let's find our Z statistic. Well, once again, it is x bar, your average, against the national average. Well, that's what you would compare, right? How much different is my average, x bar is my sample, away from the national average, 50? Well, yeah, I know they're 4 points apart. I know that. But you also have to put it in terms of a scale that makes sense. And that scaling is defined by sigma over the square root of n. And that is my Z statistic. I'll let you pause and make sure the formula makes sense to you. It is, again, x bar minus mu divided by the quantity sigma over the square root of n. If this seems shaky, please revisit my videos on the normal distribution. I'm really utilizing the idea of the normal distribution to come up with these numbers. Please go back to them if these are driving you crazy on how I got them. All right, so once we have these two pieces, then I'm ready to really make an answer. So in my steps to do, it was compute this to test, understand the problem, H0, H1, alpha, and all the data, determine the critical values, compute this test statistic. Now it's time to make a decision. And so what I see here is, again, I have the Z statistic. I'll write it down, 1.67. From here, I can now make a conclusion. Because, again, this is my number, my sample, the test statistic. This is my sample. My sample hit a 1.67 on this picture. So tell me, where does 1.67 fall? The blue region in the middle or the red regions on the edges? You bet it. It's right in the blue region because 1.67 does not exceed the 196. So my evidence or my answer here is my Z stat, my statistic, 1.67 is less than my critical value of 196. And that implies I do not reject H0. That's great mathematically. What the heck does that mean? Well, I do not reject. So let's go up and see what H0 is to see what we're not rejecting. So there, H0 was the average was 50 points. So according to my data, I don't have evidence to say it's any different than 50. Right now, yes, you got these great herbs. They might be great for things, but they're not helpful for memory according to my data. So I do not have evidence that H0 is not equal to, so H0, let me write it properly, I apologize, that H0, the average, doesn't equal 50. That's very important. In fact, so important, I want to write that in words. I do not have evidence that the true average is not 50 points. According to my analysis, the herbs are great, but they're not going to improve your memory according to my my test. Excellent. Of course, some people like to check their work. And some people don't like the critical region test as I performed. All right, the critical region test is based on an alpha, a basic alpha. Some people don't like the critical region test. They prefer, and that's why it's the next step in my testing, the p-value approach. Because you could utilize another approach called the p-value approach when it comes to making a conclusion. I call it the check. We already have a conclusion. I'm not rejecting. The p-value approach is a different approach. What it does in the p-value approach is it looks at your statistic. First of all, once again, we are two tests, so that's why the two bars. But now, we have a test statistic from your sample. Your sample was a 167. It's all about your sample. Your sample was a 167, which means by symmetry, this is a negative 167. That's your sample is 167. The p-value, by definition, is the probability we could do a sample again and get in a more extreme value. That is, what's the odds we can resample, collect data, and get a more extreme value, a more extreme sample than you have? That is the p-value. So the p-value is this total red region. That's what we got to find. If we can find this total red region, we would find the p-value. Awesome. So let me think about this. The p-value. It is the area above 1.67. I'm going to focus on that. So my p-value, what I'm going to do is I'm going to look at the area, or we can look at the area below, your choice. But, and in fact, that might be work better when it comes to Excel. So I'm actually, because we have this, I'm going to utilize that. I'm going to do twice. Because if I find the area here is the same, even though the picture doesn't show it. By symmetry, the area below here is equal to the area above here. That's why the two. These areas equal. I'm going to find the area here and double it. I can find the area here utilizing the norm as dist function. The norm as dist says, you tell me the z value, and by calculus, I will tell you the area below it. And yes, there's always a 1 because you want the cumulative effect. So, in my Excel, I could do my next step, the p-value. Well, the p-value, again, is doubled. Not always, but in a not equal to test, it will be doubled. But the p-value is double of the norm S dist. And the norm S dist says, you give me the z you're looking at, which is your z statistic. I got to be careful. My z statistic is positive. So the z statistic I want will be the negative of that statistic. Notice I put a negative sign in there. Comma, yes, you want cumulative. And there is my p-value. I would again pause the video and make sure the code makes sense to you. Why the 2? Because there's two tails. Why norm S dist? Because that's what norm S dist does. Norm S dist says you give me the bar and I'll find the area underneath it. Notice the negative I have in front of the E10. That's because the z-stat is positive, so I made it negative so that way I would get the proper p-value. And so there's my p-value, 0.0956. 0.0956. So our p-value is 0.0, one more time, 956. All right, so there's your p-value. And I'm guessing the next step in my process would be redo your conclusion. Compute the p-value, make your conclusion again. All right, so make my conclusion again. Or in some respects, let's check the original conclusion. And what do I mean by that? Well, the next conclusion you can make is based on the p-value. You see, what we do is we have this rule. If your p-value is special enough, that is under alpha, then we can reject H0. That's how we reject H0. Is if your p-value is small enough, that's what that p represents, then you are very special, you're very significant under the alpha level. But If your p-value is greater than alpha or equal to, then we will DNR, do not reject H naught. So in this example, up above, this is our p-value. I noticed right away it was greater than alpha of 5%. It was greater than alpha of 5%. That leads me to my conclusion here. So my p, which equals 0.0956, is clearly greater than alpha of 5%. And if my p-value is too big, I know that I do not reject H naught. But that's good. Whatever happens here should have already happened up here if you're running both tests. The critical region and the p-value test better match. You don't get flippy-floppy results. If you do, something is going on weird, and you should be careful of that. All right, so not only do we have one test, we have two tests. If you prefer the p-value, follow the p-value approach. If you prefer the critical value, this is the critical value approach. Together, they're awesome. You have both taken care of, the critical value and the p-value approach. Now, what are some extra steps you could do? Well, there is a confidence interval step, but that only comes if you reject. Only if you reject. And we'll explain that in future videos. Because bottom line, if I rejected, that means I don't believe in the national average anymore. That's what I think about when I build confidence intervals. When I reject, which I did not do, but if I had rejected, I would have not had confidence in this statement anymore. The national average is not 50 points anymore. So the first question in my mind is, if somebody says it's not 50 points, I'm going to ask them, where is it? With 95% confidence or 90% confidence. Where is the true national average? Again, in this question, we didn't have enough evidence to support the fact we changed the national average. So I'm not going to build a confidence interval because I did not change the national average. So nothing to look here. All right, so that step is done quickly. And then really we make our final conclusion. Well, and it always brings it back to the heart of the question. You did both the critical region test and the p-value test. Both of the times you did not reject. I did not reject H naught. And we should say at level of significance of 5%. What does this mean, bottom line? Bottom line, the herbs do not seem, because it's not guaranteed, right? I could have made a mistake. The herbs do not seem to improve memory. According to my analysis, I don't have any evidence that the herbs increased a person's memory. All right. Sometimes you get this. Sometimes you do not reject. You still should understand why and why you did not reject. All right, guys. I mean, we're done, but I like to look at the other steps quickly. That is, we didn't need to build one because we didn't reject. We have the summary. We did that. Now, there's some extras. You should always check the assumption. I'm calling them extras. I mean, you should do them. Check the assumptions. We did. We have normal right away. The problem said normal, so we got the normal. Sweet. Honestly, that's really step one. Check your assumptions. I'm saying it's extras, but really it's one of the most vital steps. Are you sure you have normal? Yeah, I said it was normal. Nice. Do we need to identify type 1 or type 2 errors? We could if you need to. I mean, in this case, what do we got? Just to go from our previous videos. So in this case, we did not reject. What that means is there's a potential of, you're right, a type 2 error. Because in a type 2 error, you do not reject, but maybe you should have. So in a type 2 error, there is a chance we were wrong. And the herbs do improve memory. All right, and that's our type 2 error. The good news, we're looking at ginseng, we're not looking at these herbs. there is no really poor error, type 1 or type 2, that is, could cause lawsuits, could cause deaths. It just, we may have not found a helpful ingredient to memory, though. So in this case, the type 2 error, again, is we could have had a chance, but we were wrong, and the herbs do improve memory. All right. It's always good to understand what you're looking at. All right, guys. So this is our first example. What I want to do now is pause the video and let you guys try to attack our second video. All right, guys, we're back. So in example 2, we're going to speed it up a little bit. So we have a report stating that SUVs were in danger of being eliminated due to the economy. A sales manager studied 40 sales of SUVs and noticed it took an average of 95 days to sell each one of them. The typical sales at the dealership for SUVs is 90 days with a standard deviation of 20 days. Is there evidence at a 1% level of significance that the true average sales is more than 90 days? Good question. So here's what we have to do, what we're working with. First of all, and I'm just going to do it all in Excel because you had a chance to write it down. Hopefully you match. First of all, we need a null. Well, the typical sales averages 90 days. So what we say here is mu equals 90. That would be the typical sales. Mu equals 90s. We believe that's our alternative, and that's always in the test. Is there evidence the average is more than 90? So are we saying the average is more than 90 now due to the economic crisis, due to the climate crisis? Are we saying SUVs are going the way of the dinosaurs? Good question. It's very important to know your alternative. Your alternative is really what you're trying to study. Really, this is the national average, the company average, and this is what you're trying to show that is different. In this case, you actually have an idea. You believe it's greater than 90. I want to make that clear that this is a one-sided test. All right, so now that I know this, I'm going to write down my ingredients. And in fact, allow me to kind of copy, you know what, let me type it. N X bar sigma mu, just to kind of copy what you have up above, alpha. So I'm still in phase 1 of my hypothesis test, right? Come up with your H0, your H1, and come up with your variables, like N. What is your N, your sample size? Let's read. Let's figure out where your sample size is. Pause the video. See if you can fill them in prior to me getting them. So what we did 40 sales. Boom. X bar. What was the average in my sample? The typical sales. That's typical. The study, notice it took an average of 95 days. So that was the study. Good. X bar is from the study. That's from your sample. Sigma, and it says sigma, the sales at the dealership is 20 days on sigma. The national average is 90 days. Got it. Alpha is the level of significance. Put it as a decimal. 0.01%. So 0.01, which is 1%. Got it. All right, so we now have step 1 completed. I do quickly notice, I'm going to throw in one of my steps, I definitely have a normal distribution. I have no clue about the sales if they're normal, but I do know because my sample size 40 is over greater than 30, that is, it's over 30, the central limit theorem kicks in, and I have normality, and that's awesome. Why do I care about normality? Because sigma. Why do I know I have sigma? Because this is the standard deviation at the dealership. The standard deviation from the company is sigma. That's not from your sample. All right? If you really want to understand the difference between sigma and S, please stay tuned for the hypothesis test when sigma is unknown and notice the differences between them. All right, so now that we have this, we go to step 2, build our critical region. Well, that's a good question. What does our critical region look like in this case? Well, it's one-sided with an alpha of 1%. Please notice that. It's one-sided with an alpha of 1%. So, let me put a big old gash in here. In example 2, we are one-sided. Boom. And it is the upper bound because we are a greater than. That's why I always know my alternative. My alternative really controls my critical region, right? This right here, let me highlight it in red, and alpha control what my critical region looks like, my critical values look like. Those two pieces control my critical value. First of all, it's one-sided because I only care about the greater side. Because it's one-sided, all of alpha goes into that. I can't state that enough. I don't divide it by 2. I shove all of alpha to the one side because there's not 2 regions. How do I know there's not 2 regions? I read the question. It is about greater than. So this is the value I want. What is the z-value that traps the top 1%? Better known, it is the z-value, norm S inverse, right? Because that finds the z-values. It is the z-value that captures the bottom 99%. Boom, 2.32. So that would be my critical value. And in this case, this is the only critical value because of the fact we are looking at a one-tailed test. There is only the upper critical value because we had a one-tailed test. That's extremely important to me. All right, time to crank out the z-statistic. What about your sample? Where is your sample? Well, your sample is defined just like the previous formula, though I can't use it because I've adjusted a little bit. It is, but I can write it again. It is x bar minus the mean divided by the quantity of the standard deviation sigma over the square root of n. And there's our formula. And there's our z-statistic, 1.58. So you see, we have a bar at 2.33. That's the bar. And if you get to this side of the bar, you get to reject the null. You have evidence things have changed. If you're staying on this side of the bar, there is no evidence. You do not reject H naught. And that's really the game. Where do you fall in your sample? And so when I take my sample, the Z sample, and I calculate it out, my statistic is a 1.58. I can clearly see my number is less than this number. My number falls in the do not reject region, and I am done. All right? Here's a step. Here's a step. So my final step is to compare them. My statistic is here. It is not greater than, so it does not fall in the rejection region. And that's what I'm going to say. I do not reject H naught. My stat, which is 158, is less than the critical region. The critical value, which is 2.33. Simple enough. I don't have any evidence to support the fact that SUVs are going the way of the dinosaur. So what, in our sales recently, it's taking a little longer to get them off the lot. It's not long enough for me to worry about it. That's the key. So it's taking a few extra days. Next month, it'll take a lot less, all right? That's the key, is we have some variation. We have some room to wiggle. And so that's what I get. I can clearly see my statistic is not bigger than this critical value, and that's why I'm not rejecting. So I definitely do not reject. The DNR of H naught is right there, if you want to put it all in Excel. All right, we can check with the p-value, or some people prefer the p-value. You got to understand the p-value to really understand, though, how to build it in this case. So the p-value is based on your sample, 158. The p-value, so this is kind of like a check. Let's run that p-value again. The p-value is your sample, not this arbitrary alpha somebody gave you. Your value is 158. That's you. That's your number. You tested it, it's your number. The p-value, by definition, is the chances somebody can repeat this test and get a sample more extreme, i.e., the p-value is, once again, the area outside of your statistic. So in this case, the p-value is, well, let's go to Excel. Let's think about this now. How would I get this p-value? You're right. You got to use the norm S dysfunction, but you got to be careful. I'm going to 1 minus, because I want the area above, the norm S dot dist of the z value, where's my z statistic, comma 1. And yes, it is always comma 1 because you want the cumulative distribution to calculate the integral out. The norm as dist finds the area below. You want the area above, which is the area more extreme in this case, and that's why the 1 minus. Please notice I'm not doubling this number like I did up here. The doubling was because of the not equal to. A two-sided test, that's when you double. Notice the 2. This is a one-sided test, no doubling. This was a greater than test, that's why the 1 minus. You really have slight adjustment with each test we do. Two-sided, you do have to double. One-sided, you do not double, and you just got to be careful. So my p-value is 5.69%. So that's my p-value, 5.69%. Well, I can tell you one thing. That's definitely greater than alpha that somebody set down at 1%. And if you're greater than alpha, my conclusion is IDNR. I do not reject H naught. All right, guys? Again, if my p-value is not special enough, and that's the idea, my sample is not special enough. The speciality of the sample was 1%. It was set down, it's a 1% chance. My sample has a 5.69% chance of another sample being even more extreme. So even though it's 5.69, which is nice, it is not smaller than alpha. So I do not reject H naught. That's the idea. This number has to be less than alpha for me to reject, and it is not. This number is bigger than alpha. It's always smaller the p-value, the better. So bottom line, I do not reject. So some quick finishing thoughts. Confidence interval? Nope. If you don't reject, you don't build a confidence interval. 2 assumptions? Sure. My assumptions are met because n equal to 40 is greater than 30, and that kicks in the central limit theorem, and that's really the only thing I care about. There are other assumptions you have to watch out for. Let me go to my step sheet, as I call it. I like to have this because I also like to take a picture of it so I know some of the key pieces to each hypothesis test. And we are at this stage right now, the single sample for mean with sigma known. What you need is a random sample. Well, I hope the person that collected the data did it randomly and representative, because if it's not, we have biased information and we're crapped. I don't know that, but I hope they did. And the one thing I can control is normal or central limit theorem. In the first example, we got normal for free because we were looking at an IQ test, a memory test, and those are standardized and those are normal. In the second example, we had to enforce the CLT, and we got lucky. We sampled enough to make sure we had the CLT and get normality, and that's awesome. All right, guys, bottom line, in example 2, we don't have evidence that SUVs are in danger. We don't have evidence they're taking longer time to take off the lot. It's just a bad month. The next month will probably be better. But as of right now, I have no evidence to reject, which means, as far as I could tell, it's still taking about 90 days. All right, guys, thank you for watching this video. Stay tuned for more.